तो देखिए फर्स्ट लॉ जो इक्वेशन है, now we are putting it in different forms. They're very simple, but you must know the difference between them. So we are making first division, that is we'll be talking about macroscopic energies, and they come into play when the system is moving. So when the system moves, there is a kinetic energy as well as potential energy which comes into play. So if you are talking about a system which is having macroscopic energies, then we will use the equation, sorry, Q minus W is equal to delta E, where your delta E this delta E is actually equal to delta U plus you have kinetic energy and you have potential energy and plus rotational energy. So okay, let me take the second diagram here. So when we talk about delta E is equal to delta U plus delta and all of this kinetic energy plus potential energy plus rotational energy, and they are macroscopic. That means they are part of the system as a whole. It's because of the velocity of the system, because of the position of the system, because of the rotation of the system. And we are not talking about the velocity of molecules, position of molecules, or rotation of molecules. We're not talking about that. That comes here in delta U. We have already talked about it. So if these energies are into play, our equation gets modified and our equation is Q minus W is equal to delta E. Okay. And if our system is stationary, then the same equation can be written like this. Okay. Now, if you want to write in specific parameter, that means you can divide both sides by mass. Now, you know, mass is a closed system, so mass remains constant. If you divide by mass, you will get this equation Q minus W is equal to delta E, and all will be small letters, which means energies per unit mass. Okay. And if you are talking about a stationary system, it will be Q minus W equal to delta U. Okay. Then you can also divide by time. So then we will get in terms of rate. So the same equation, because time is same for all the energies, whether you are talking about Q, W or delta U or delta E, the time interval for all of them are same. So you can divide by the same time interval, you will get the rates, and for the stationary you will get this. Okay. Then you can divide both by mass and rate simultaneously, and you will get this specific rate minus, so heat given per unit mass per unit time minus the work done by the system per unit mass per unit time equal to change in total energy of the system per unit time per unit mass. Okay. And same thing you can do for this. Okay. Now, if the system is cyclic, then you know that delta U will be 0, and you can write Q minus W equal to 0. Cyclic means the system has come back to the same state. which means U is going to be same. Okay. Now we can do this law in differential form also. The same law can be written in differential form also. Now, the fundamental behind that is that we have applied first law to the complete system, right? But we can also apply to any part of the system. So you can take out any particular mass or volume of the system and apply the first law there. You can do that. And then what will be required? It is something like this. If you have a system like this, right? You are applying first law to the whole system. What you can do, you can take a section of it, part of the system. Right? And again, you can do the same thing. You can find what is the energy going in, heat going in, work being done, right? Delta Q, delta W, and then you can find what is change in your internal energy oblique change in kinetic energy. You can find. So if you want to consider a part of the system, you can do it. You can, only thing you'll have to make it a system and you'll have to find out what are the energies going into that part and what are the energies coming out from that part. So if you are taking a part of the system, similarly, when we talk about times, we apply between T1 and T2, right? But this law applies between any interval of time. So if you are applying in a finite interval, it doesn't happen like that कि बीच में total energy बढ़ गई और बाद में end में आके कम हो गई. At all the times, total energy will remain conserved. So it cannot happen कि बीच में suddenly energy बढ़ गई, law of conservation fail हो गया और at the end of the time जो आपका observation का time है, at the end of the time फिर बाद में जो है सब conservation law valid हो गया. नहीं. Whatever small time interval you select, you will find that the law applies in that also. So that means you can break the whole process into small interval of time also, and you can still apply the equation of first law. Okay. So if you are taking a small system, you will get del Q minus del W is equal to delta E. And if your small volume is approaching to 0 or time is approaching to 0, you can write it dE. Okay. It's only a way of writing it because Q and W are not properties, so we do not write D before them. So dQ is wrong. We write del Q. Okay. So only thing what you have done, you have taken the first equation and made the time interval very small, or the once, or you have selected only a section of the whole system. Then you will get del Q given to that part of the system minus the work done by that part of the system will be equal to total energy change of that system. Okay. And if your part is so small, infinitesimally small, you will write it dE. Otherwise, you just write delta E. Okay. And same thing for stationary system. If the system is not moving or that part is not moving, you can write it like this. Okay. Same thing you can do in terms of specific parameters. So now again the mass you are selecting, the part of the system, the mass of that part of the system is also constant. You are talking about closed system. It's not an open system. So you cannot change the mass of that. So you can divide by mass, you will get this. Same thing. You can divide by that mass of the system also, or the part of the system. Okay. And similarly, if you write in terms of rate, now it would be like this. Q dot minus W dot is equal to E dot. Okay. And if you are doing both, dividing by both, it will be this. So either you are taking part of the system or you are taking part of the process, the first law applies. Okay. Now, so we have some more observations about first law. It says that first law does not impose any restriction on the path by which the system moves. When we are moving from state 1 to state 2, I told you there are two types of processes. One is quasi-static process, and the second one is non-quasi-static process. And we drew the diagram like this. We want to move from state 1 to state 2. Right? In one case, it is a quasi-static process, and the other process path is non-quasi-static process, which is shown by dotted line. When it is shown by dotted line, it means that on this path we don't know the state. When it is shown by complete thick line, right, then it means that all the points, the state of the system is known. That is the difference between. If you are moving very slowly along a quasi-static process, that means at each point the state of the system is known to you. But if the process is going abrupt and you know only the initial and final state, like explosion or accident, right, in between what is happening you are not unable to measure, then you show it by dotted line. Now, what the first law is saying, that whatever the path is, whether you have a quasi-static or non-quasi-static, okay, the first law holds good. Okay. The only requirement is that we shall be able to measure heat given to the system and work done by the system as it moves from state 1 to state 2, and internal energy of the system at both the states. So if we are talking about either the full process or we are talking about the path of the process, what is required is that you should be able to measure what is Q, what is W, what is delta U, either 1 to 2, or if you want to measure it from, let us say, A to B. These values should be known to you. Only then you can apply first law. Right? तो फर्स्ट लॉ इज नॉट सेइंग कि भाई आपका पाथ ऐसा होना चाहिए या वैसा होना चाहिए. वो जो रिस्ट्रिक्शंस हैं वो सेकंड लॉ में आती हैं. ठीक है, we will talk about them later on. Okay. Then another thing, the first law does not deal with or give the absolute value of internal energy. In the first law, there is nowhere we are talking about U or E. We talk about delta U and delta E. Okay. And even if you have to take the, because you will say then we know U1 and U2. No, we do not really know what is U1 and U2. We talk about delta U, let us say it is equal to U2 minus U1. You would say that unless until we know U2, we will not know U1, or unless until we know U1, we will not know U2. No. What you are doing is basically a reference frame is being fixed. एक रेफरेंस फ्रेम होता है जिससे आप U1 निकालते हैं और U2 निकालते हैं. So U1 and U2 are not absolute values, they are with the reference. So let us take the example of let us take a duster, this duster. If I talk this table, then the potential energy of this duster is 0 here, and I pick it up, it is some value. Okay, but then I can shift this level to this ground. Then even when it is lying, it has some potential energy. So in one reference frame, this was having 0 potential energy, and in another frame it has more potential energy. And you may say that, okay, let me put it there on the ground, but then again we are on the second floor. You can go down and say that, okay, the ground floor is the reference frame. So then even when it is lying there, you find that it has some energy. So what has happened? As you change the reference, your energy. Same thing is true about kinetic energy. You are sitting inside a train, and your luggage, your body, yourself, you are moving with the train. You may say very well, you can close the window and say that our kinetic energy is 0. For a person who is standing outside, you have a very high kinetic energy. Or for that matter, you are on the earth, which is revolving like at a very high speed and going around sun. For you, the kinetic energy is 0. But the moment you go out of earth in space, you will find that you have a lot of kinetic energy. So your energy is based on the reference. This is what I was talking about, macroscopic energy. Come to the microscopic energy. You may not consider nuclear energy at all because it is not coming into play. So you may consider only the thermal energy of the molecules, because no chemical reaction is taking place, no nuclear reaction is taking place, no change of phase is taking place. But does that mean there is no such energy? Nuclear energy is also there, chemical energy is also there, phase energy is also there. But because they are not coming into play, you are not talking about them. Okay. So in the ultimate sense that you do not know what is the total energy, total or internal energy, absolute value of the energy, that we do not know. So we fix a reference, start from it, measure the energies, and then we find the change in energy, and we might find the sex. So we have U1, okay? We do the calculation, we find delta U, and that gives us U2. But U1 and U2 are subjective, they are relative to a given frame of reference. What will not change is U2 minus U1 will not change. Okay, so this is now we come to heat and work. So if you look at your equation is Q minus W is equal to delta U. Okay, so we must be able to calculate Q and W before we can do anything with delta U. If we want to apply this equation, we should be able to find out Q and W. Now heat flow, there are three methods: conduction, convection and radiation. And you have formula for them. You can find how to find the heat transfer. Okay. And that will depend upon the case to case. You can see for conduction we have Fourier's law, then convection we have, and radiation also we have equations for that. Use those equations, you can find what is the heat transfer from one body to another or system to surrounding. Okay. Now what is we are discussing? So this you can do it yourself, or the heat transfer course will be telling you about it. And of course in the junior classes also you have done something about it. We don't want more than that here. Okay. Then we talk about work. Now all this also you have done, but still I am mentioning it here because there are many different types of work. In a many different forms the work can take place. So I am just summarizing them here. The first one of them is electrical work, and this is written as like WE is equal to integral VI dt. V is the voltage across which the current I is flowing for duration dt from T1 to T2. Okay, how do you get it? You see for yourself. Okay. Then gravitational work, and that is equal to Wg. You can put the subscript Wg here. It is equal to mg Z2 minus Z1. Okay, change in potential energy is the gravitational work. When a potential energy is changing, gravitational force is doing the work. It comes under the category of work. So potential energy and electrical energy, work done by the electrical energy, they come in the work category, not in heat category. Okay. Then we have acceleration work, force into displacement, and final equation you get acceleration work. This is also same as kinetic energy change, half m v2 square minus v1 square. Okay. And how do you get it? You take this equation, work done is equal to F dot dr, and you can solve it. So I have it here, but you have to do it yourself. Okay, these are the steps. How do you get acceleration work is equal to this, and it is coming from F dot dr integral. Okay, or you get finally this answer, kinetic energy change. Then we talk about spring work. You would have heard, and spring work is basically when you have a spring, you expand it. It is a spring work, and actually that work is what you are doing is the bonds between the molecules and molecules. You are stretching that molecules. So it's sort of a intermolecular force that is doing the work. Okay, and it is stored within the spring, because when you do the work, what happens? The external force is doing work and the spring get extended. Okay, and once you leave it, it goes back, okay, to its normal position, and that work is equal to, spring work is half k delta x square. You know it, okay. When you calculate spring work, if you calculate in terms of the external force, then you are applying the force. Either you are saying that I am applying the full force, so you can, their confusion comes in because, let me clear you if you have doubts about it. Suppose this is a spring here, and you apply here force F, okay, and this displacement is delta x. So what work you are doing is F into delta x, okay. But when we will apply F delta x, what will happen? This spring will be stretched to a longer length, because the spring can store only half kx square. Because spring force is actually, if you call spring force, that is equal to minus k delta x. So you apply a full force, but the spring is applying force equal to minus k delta x. So the energy stored within the spring is k delta x square by 2. Okay, but the remaining energy gets in the, you can say, kinetic energy of the spring, and spring keeps on oscillating, and finally it gets dissipated, it gets converted to heat. So you should be careful about it. How much the external force is doing the work, how much is the spring doing the work. So if I apply Fx force on any spring, I have done the work this much. Work done by external force is F delta x. What is stored is this much. The remaining, the balance is gone into kinetic energy, and then it gets into heat. This is what happens. So you should know that what you are taking care of, right? Otherwise calculations में गड़बड़ हो जाएगा. Then we have elastic bar. It is same as spring. The only difference is spring is coiled, so the deflection is very high. But you, if you extend a bar, then the displacement is very small, and it comes out to be strain energy, which is there, Ws strain. This is half sigma epsilon volume of the bar. This teacher of your mechanics should be teaching you also solid mechanics, where they are talking about energy stored within solid bodies due to deformation or extension. Okay. Solid mechanics course may be in the next year or next semester, but all these you have done before. Elementary you have done, right? There you will talk about three-dimensional deformation. Here, one-dimensional deformation you can take, or you can take it like this. So same thing as you do for the spring, same thing you do for it here. Okay, and you get the same thing. Okay, and it is only written in terms which are used in your solid mechanics. One is epsilon is the strain, or sigma is the stress. Okay, and if you do it, you can do it and you can get it like this. Finally, you get strain per unit volume is equal to half sigma epsilon. And how this energy is stored is something like that. Suppose you have a bar, you bend it. Okay. So this energy is stored there. You extend a bar, this energy is stored there. Okay. If you have a iron, you can say rope going along, and you hang over it, it gets extended and the energy is stored within that wire. This is called strain energy. Okay. So elastic deformation, same as spring. The spring is also strain energy, and deformation of, you can say, solid bodies is also stored as strain energy. This all is there in Sengel and Bowles, you can see there. Then there is another form of energy, surface tension, and this is equal to sigma is surface tension here, and the change in area. You would have also read about it. So what is the surface tension? What is the change in area? And that energy is stored in the surface. So if you have a balloon, some of the energy is stored in the balloon surface also. Okay. And this is how you do it. You have a frame where some liquid is, film is here. You extend it, right? And you get increase in area. You would have read in your secondary classes that if you have a drop, then there is only one surface. If you have a bubble, you have two surfaces. So you can find how much energy is stored in a bubble or in a drop. Same thing here. Okay, surface tension. Then shaft work. So not only a force by extending, you can do the work. You can do the work by rotating. And all these come under the category of work. Force multiplied by displacement. They are all under the category of work. That's a different thing, that when that energy is not stored or dissipated, it will get converted into kinetic energy and then thermal energy and so on. Thermal energy is the last, you can say, repose. But they are all form of work. So if you are doing this problem on thermodynamics, you have to see that whether they will fall in work or they will fall in heat category. And this is also same. You will see that all these formula except for electrical energy, even electrical energy, you can say that force into displacement will be there. But all other forms, you have directly force into displacement, that gives you the work. Okay. And this is F R d theta, and finally it comes out to be tau theta. So what is the torque you have applied and how much rotation you have given, that is equal to the work done. Okay. Now then we have displacement work, which is you can simply have F dot dr. Okay. Right. So all these works can be there, but now comes a special one where you will make lot many mistakes, and it is not clearly mentioned in the books. So I would expect you to give more attention to this. Now this is called expansion work, and we are talking about change in volume of the body. So the formula here is, you see, what is the work done by the system on the surrounding. If you have to calculate that, now let us say I have a system here and it is changing its volume. Okay, now there is some pressure here and there is some pressure here. These two pressure are different. Or let us take example of a cylinder, right? This is the external force or external pressure, let me take, because we will talk in terms of volume multiplied pressure, and there is a inside pressure. Now what will happen, that let us say your piston is moving to the right. Why? Because P external is less than P, right? So it will do some work. Now what will happen is, there are three possibilities. You can say possibilities are P external is less than and very nearly equal to P. P external is greater than or very nearly equal to P. And then there is P external is less than P or P external is greater than P. So four possibilities exist. Two are that P external more than or less than. And the two possibilities are that it is slightly different or it is significantly different. Okay. Now we will leave this this one and this one. We'll leave this for the time being because it's one and same thing. The piston is going in or piston is coming out. P external is more or less, right? So we begin with P external is less, so the expansion is taking place. Now this case is actually P is equal to P external, and in this case P is this case, second case, ये वाला P is greater than P external. तो हमारे पास दो केस आ गए, ठीक है। जो थोड़ा सा डिफरेंस है प्रेशर में, क्योंकि some minor difference is required for the piston to move. If both are equal, they will not move. So we assume that they are slightly different, such a less difference that they are equal. And if there is a very small difference, what will happen? The piston will move very slowly. So what will happen is, if you now let us say what are the work done? The work done by the system you can say it is equal to P into delta V. But work done on the surrounding will be equal to P external delta V. So the system is doing work because it has pressure P multiplied by delta V, that is the work done. But surrounding is opposing it only with a little less force. So it will receive the work equal to P external delta V. And there will be difference between the two. You can say this is, let us say this is equal to P system and this is. Where is this difference gone? What is happening to the difference? System is doing work P delta V and the work transferred to the surrounding is P external delta V. And there is a some finite difference between the two. So the system is doing more work and the less work is going into the surrounding. Where is the remaining work? Which work we should take for our equation? Yes, anybody? Hmm? Kinetic energy of the? Yes, yes. There. So what has happened is you have a piston which is a force here P into area and there is a force acting on his P external into delta area. Okay? And what will happen? This will get a velocity. So the extra work gets into the piston. Now if piston is massless, what will happen? Finally, piston is going to stop after the expansion has taken place. What is happening? What is happening is the molecules here get kinetic energy. So the work which is transferred to the surrounding is P external delta V only. The remaining work which the system did got transferred to the molecules of the system itself or to the piston. And if you are considering piston as massless, or finally the piston stops, where that energy is gone? Into the molecules. Alright? And those molecules can be outside of the surrounding or they can be inside. Even outside molecules will get the velocity. Kinetic energy. So when you talk about what is the work done by the system on the surrounding, it is P external delta V. And you have to take into account what is the balance. If the balance remains in the system, right? So what will happen? That kinetic energy will slowly get dissipated in the form of heat and that's gone. Within the system, it's not going out. We have only to bother how much of work has gone out. What remains within the system is not gone. So what has gone out? The surrounding has been displaced and some work has been done. It is P external delta V. And you can say, okay, further, because the piston is accelerated, it is displacing the molecules of the surrounding and they are getting displaced, they are getting kinetic energy. Okay, some kinetic energy is gone there. So you add it up into the system work done by the system on the surrounding. But of course, these small things we cannot take care of. So what we do, the remaining work remains in the system. Okay. So you have to calculate what is the work transferred from the system to the surrounding. So, okay, one second. So the real formula is P external dV. Okay. Now what happens is, when it is a quasi-static process, it becomes P dV, and we jolly well nicely all the time apply this formula. But remember, there is a condition that internal pressure and external pressure are same, the process is quasi-static. If the process is not quasi-static, if the process is abrupt, if the outside pressure is significantly higher or lower, then the equation will be used this one, not the other one. Okay. So this is what you have to take care of. Now, when we talk about this equation, we must know P external, then we can simply solve it. But if you are not knowing that, or let us say you know that P is equal to P external, then you can have this equation, and then there are number of formulas for that, isothermal expansion, polytropic expansion, isentropic expansion, what will be, because what has happened, you have converted external pressure into system pressure. Now system pressure is related to other properties, so you can do that and you can derive the formula for that. So if you are using any of these things, be careful. First thing to check is whether the process is quasi-static or non-quasi-static, whether the external pressure is same as the internal pressure or not. If they are not same, you have to use external pressure. If they are same, then you can use internal pressure, and accordingly you can use other equation, because you know the equation of path, that isothermal, isochoric, isobaric, isentropic, we will do that, polytropic, so that will also come into play. So here we will stop. You had some question? Yes.